So in this video, I'm going to give the final review for the linear system control class. Okay, so I'm going to go over all the solutions for the questions I posted for the final review. So let's get started with the first question. The first question is about the eigenvalue and eigenvector. So the first question says, if A is, for a matrix A, if a little a is an eigenvalue of A, okay, with an associated eigenvector which is new, and so the question is, what is an eigenvalue of b times a squared plus c times a? So here, of course, I assume b and c, they are constant. And with an associated eigenvector of what? Something. Okay, that's the question. So basically we can use the definition. So the definition of eigenvector says, if A is eigenvector of A with associated eigenvector nu, I can say A times nu is A times nu. So this is the eigenvalue. So this will be the eigenvalue and this will be the eigenvector, basically. Okay. Now, based on this one, now what I can do is I can use this property. Say if I do a squared times nu, which is a times a, I just write out the a squared as a times mu. A times u, use the property over here is a times mu is little a u, and I can move the little a outside. A times u, and this guy we use the property again, so which is equal to a times a u, which is a squared u. Okay, this is one state. You can see we already down over here, somehow over here. So if I do b times a squared u, which is apparently is b times a squared u, we can also follow the same property if a mu is equal to a mu, okay? So if you times c on both sides, c is a scalar, okay? So the c, okay, that's the same. So if you do the sum and sum, that should be equal, which means I have ba squared plus, this gives us plus mu plus ca mu. So I can move this together as plus ca times mu, which is equal to ba squared mu plus ca mu. Of course, I can also merge them together, becomes ca times mu. So if you look at the structure, we can say this is the matrix we're talking about over here. It times something is equal to some value times this vector. Okay, so apparently this is eigenvector. According to definition, this is eigenvector of this matrix, and this is eigenvalue. So we can see over here. Here we say is ba squared plus ca is eigenvalue of this guy, and as associated eigenvector is still nu over here. Okay, the first question. So let's move to the second question. The second question talk about a span, dimension, and basis. Okay, so it says I have given a couple of vectors. Is x1, which is 1 0 0 0. x2, which is 1 1 0 0, x3, which is 2 0 2 0, x4 is 4 2 1 3, and x5 is 3 3 3 3. So that's my 5 vectors. So my question is, what is the span of x1, x2, and x3, x4, and x5? Okay, equal to what? And what is the dimension of the span? x1, x2, x3, x4, x5. Okay, and last question is, what is the basis of the span of x1, x2, x3, x4, x5? So basically, okay, let's start with the span. Span basically talk about it. If you do a linear combination of all the vectors you have, then what is the sort of the domain or the space they can reach by doing the linear combination. So but apparently this is given by somehow like alpha 1 x1 plus alpha 2 x2 plus alpha 3. You just do all the possible combinations of the linear combination of the vectors x4 plus alpha 5 x5. So here alpha I is a scalar. It's not a scalar, doesn't matter, it's positive or negative. That's the span, which means you do all the possible combinations, see how this linear combination can reach what kind of domain for it, what kind of domain can reach. Okay, so that's the span. Dimension of the span, which means how many of the linear independent vectors you can find from this phi. That's called the span of it. Okay, so this one, if you look at this one, so x1, x2. So first of all, how many of this one maximum linear independent vectors I can find among the phi? So first of all, x1, x2, they are linear independent of each other because this one only has a non-zero over here, first entry. Now this one, the second entry is a non-zero. It means it doesn't matter what vector you give for x1, it cannot form x2, which means x2 is linear independent of x1. You can also follow the same logic. So x3 is a linear independent of x1, x2 because I have 2, 0, 2, which means the third entry is non-zero because x1, x2, they all have non-zero. I have 0 entries for the third entry. So the linear combination of the two cannot give you a non-zero entry, a third entry. Okay, so do the same thing for the fourth one. Also the x4 is also linear combination of the first three because the last entry is non-zero. Well, for x1, x2, x3, their last entries, they're always 0. So it doesn't matter what linear combination you do, you cannot get the x4, the non-zero, the fourth term. So which means x4 is also linear independent of x1, x2, x3. So this I can say, is this 4 are linearly independent? Okay, how about x5? Can we have more than 5 linear independent vector for a 4-dimensional? Because this is a 4-dimensional vector. So for a 4-dimensional matter, you can only have dimension 4 or less. You cannot have 5, right? That's the property. That's why, because I already have 4 linear independent vectors, I cannot have more than 4 linear independent vectors for a 4D. This is a 4D vector, which means this is equal to 4. Okay, the basis is trying to figure out what is the linear independent vectors. Is basically this is trying to say what are the, trying to just give me a set of linear independent vectors. So if it is a 4, you find a set of 4 linear independent vectors. Okay, so according to what I mentioned here, I can say, hey, this is a x1, x2, and x3, and x4. There's a set. This is a set of bases. Of course, this is not unique. You can also say x1, x2, x3, and x5. That's also okay, right? Okay, so basically for basis is not unique. Okay, so let's now move to the third question, which is about the matrix property. Okay, so the question says, if I give you a matrix B, which is 1, 0, 3, 1. Okay, this is non-symmetric matrix. So first of all, what are the eigenvalues of A? Oh no, sorry, B. And the second question is B positive definite? Okay, so eigenvalue is fairly straightforward. Eigenvalue is computed by first finding out the characteristic equation, which is given by determinant of lambda I minus b. You can also do lambda I b lambda determinant of b lambda minus lambda I, which is the same. You set it 0. This is called characteristic equation. Okay, so the determinant of lambda I is, because this is 2 by 2 matrix, your identity matrix has the same dimension of B, which is lambda times identity of 2, which is lambda 0 0 lambda minus 1 0 3 1 equal to 0. Okay, I can put them together, which is the determinant of lambda minus 1 0 negative 3 and lambda minus 1 set to be 0. Okay, the determinant says is computed by the product of the diagonal entries minus the product of off diagonal entries, which is lambda I times lambda I, which is lambda I squared, and minus this 0 times negative 3, which is minus 0. So just ignore that, it's equal to 0. So I have an eigenvalue is 1 and also 1. I have two eigenvalues, they are both equal to 1. So the second question is be positive definite. Okay, when we say positive definite, the condition is, okay, this one, so generally speaking, we say positive definite means x transpose time. Okay, I use B is positive definite if and only if x transpose B times x is equal to, is greater than equal to 0, is greater than 0 if x is not to 0 0, not equal to, and x transpose B x equal to 0 if x is equal to 0 0. That's called positive definite. So that's the definition. And the actual condition you can check is, okay, this one set, it doesn't matter B is symmetric or not, that's the definition. However, if B is, it determines, okay, if B is symmetric, okay, just do over here. So this one comes down to the actual condition, we can check the eigenvalues. So this becomes if B is B plus B transpose divided by 2 is has positive eigenvalues, then B is positive definite. So this one I mean by, if B is symmetric, this one you can also interpret this as if B is symmetric. In other words, B is equal to B transpose. This becomes simplified as if the condition becomes if B has positive eigenvalues, then B is positive definite. Okay, so if not, you have to use this condition. Okay, so generally you can just compute B plus B transpose divided by 2 to check if the eigenvalues, this B plus B transpose divided by 2 has positive eigenvalues. Yes, it's positive definite. So now it's not positive definite. So if you look at this one, so you cannot, even if the eigenvalues B, they're always positive, you cannot check this direct. You cannot reach the conclusion directly unless B is symmetric. Unfortunately, here B is not symmetric. Okay. So I cannot say, because this one, if this is 3, it's symmetric, but it's not. So if it's not symmetric, I cannot use the eigenvalues of B. I have to check the eigenvalues of B plus B transpose divided by 2. Okay, now let's do that. So let's compute B plus B transpose divided by 2, which is equal to 1031 plus 1301. That's the transpose. Okay, which is equal to 2332 divided by 2, which is equal to 1 3 over 2 3 over 2 and 1. Okay, we just have to check the eigenvalue of this guy. Okay, all right, let's check the eigenvalue. Again, is computed by finding the characteristic equation, which is determinant of lambda I minus B plus B transpose divided by 2, which is set to be 0. Okay, the determinant, this guy will be just determinant of lambda 0 0 lambda, then this is just 1 3 over 2 3 over 2 and 1. Okay, set to be 0, which is given by, okay, this is determinant of lambda minus 1 3 over 2 negative negative 3/2, and then lambda I minus 1 set to be 0. Okay, so this one is lambda minus 1 squared minus 3/2. The negative will cancel out. Okay, times squared equals 0. Okay, so this one, let's do this one. So this one becomes lambda squared minus 2 lambda plus 1 minus 9/4 equals to 0. Okay, which means I have a lambda squared minus 2 lambda plus, this is 5/4. This has to be minus 5/4, basically. Okay. So the eigenvalue, this can be written as lambda minus 1/2 times lambda plus 5/2. If you do the computation, okay, it's set to be 0. So I have lambda is 1/2, and lambda 2 is negative 5/2, which means one of them is positive, one is negative, which is doesn't satisfy the condition, because the condition set has to be, all eigenvalue has to be positive. Okay, so this is not positive definite. Okay, that's question number 3. Okay, let's move to the question number 4. Okay, the question number 4 is to compute the transition matrix of linear time variant system. So I give a linear time variant, which is x dot t is negative 1, 0, 0, e to the t times xt plus e to the minus t 0 times u sub t, and the y sub t is 1, 0 times xt. So that's my given linear time variant system. So the objective is to compute the transition matrix phi t and 0. Okay, so the transition matrix is actually only determined by this matrix A. This is my matrix A, this is B, and this is C. Of course, this is A sub t, right? B sub t. You can see it's A sub t. So the transition matrix is typically given by the Pino-Baker series, right? So Pino-Baker series, the general one is the Pino-Baker series. So it can be complicated. So that's the standard form is Pino-Baker series. So it's only determined by A sub t. You use only Pino. If you want to know the Pino-Baker series, you can check my previous lecture notes on the solution of the linear time variant system. Now, for Pino-Baker series, talk about a general case. For a special case, if A sub t is diagonal, so the Pino-Baker series just becomes this. The transition matrix is just given by t and 0 is just integration by, it's just exponential of integration from 0 to t, whatever I change the function here to tau. Okay, but this is constant, is negative 1 d tau. 0 is still a diagonal one. The transition matrix is still diagonal, and the diagonal entry is given by the exponential of the integration from 0 to t. That's determined by this one. Okay, the transition matrix from t to 0. Okay, so if you change this one t from t to tau to maybe t0, t0 for example, you just integrate it, you change this to t0, this to t. That's okay. You just change that. Now here you have to change every function here to its tau. It's like e tau. So this is et, you change it e tau, d tau. That's it. Okay. So of course when you do this t to t0 to t, this becomes t0 to t. So that's lower bound, upper bound. So that's it. That's the transition matrix. Okay, you don't have to do a lot of the complex computation of the Pino-Baker series. Okay, so if I do the integration, so I have here is e to the integration. This guy is negative t, right? Negative tau. Sorry. Integration. This is a 0 to t, 0, 0. This is a e. The integration of e to the tau is still e to the tau, and 0 to t. Okay, so this one becomes. So this guy is e minus t minus 0. So it's 0 is minus t, 0 like this. This guy is e to the e. When t tau is t is e to the t. When tau 0 is minus e to the 0 is 1. So, Okay, so that's my transition matrix. Okay. So the next question number 5 is about the stability of the linear time invariant system. So given linear time invariant system x dot t, which is -2 0 0 0 -3 0 0 0 0 xt plus 2 and 3 0 times u sub t, and my y sub t is equal to 1 1 1 times xt. So that's my linear time invariant system. You can see this is my A, B, and C. Okay. So my question is this system BIBO stable? Is the system marginally stable? Is the system asymptotically stable? Okay, that's the three stability problem I mentioned in class. Okay, so let's take a look at the BIBO stable. Okay, the BIBO stable, the condition is, so the sufficient condition, so let's talk about a sufficient condition. Let's do this one. BIBO stable. Okay, so a sufficient one is if all eigenvalues of my matrix A have negative real parts, then yeah, it's BIBO stable. Okay, and if this is not the case, if all eigenvalues are not, some eigenvalues have positive or zero real parts, then you can go to the second one. It's called necessary and sufficient condition, which is if the poles of each component in the transfer function have negative real parts. So that's the one you can always check. That's the necessary and sufficient condition. Okay, so that's the first one. If I look at this one, so first of all, the eigenvalue, because this is diagonal matrix, so the eigenvalue is determined by the diagonal value. This values on the diagonal entries. So the diagonal entries are given by -2, -3, and 0. So like eigenvalues are -2, -3, 0. Unfortunately, one eigenvalue is 0, which means it has 0 real parts. So this one does not apply, apparently. So I have to go to the second part, necessary and sufficient, which means I have to check the transfer function. So the transfer function is given by CSI minus A inverse times B. So that's the transfer function. So I just replace everything. So C is 1 1 1. Okay. And SI minus A, so I is an identity matrix. Okay, so identity. So because the size will be compatible with what dimension we have for A. So because A is 3 by 3, so the identity is also 3 by 3. So which is S 0 0 0 0 0 0, right? Is minus A. So because A is also diagonal, so it's just equal to S minus diagonal, S minus 2, so S plus 2 0 0. This is S plus 3, and this is still 0 because S minus 0 is still 0. This has to be inverse time matrix B is given by 2 3 and 0. Okay, alright, so the inverse of a diagonal matrix is just be given by this is 1 over S plus 2 0 0 0 1 over S plus 3 0 0. This is 0 0, this is 1 over S times 2 and 3 and 0. So if you calculate this product, I won't go to very detailed one, but we can do the product. What it comes up is this becomes 2 over S plus 2 plus 3 over S plus 3, which is I can write this as 5S plus 12 divided by s plus 2 and s plus 3. Okay, so it turns out my transfer function only have one term. So I just want to figure out, yes, this term, the eigenvalue, the poles, with the poles of this term, each term have negative real parts. So poles are actually determined by the denominator. If you set the denominator to be 0, that's how you compute the poles, right? And the poles are given by s minus 2 and s is minus 3. So apparently the poles have negative real parts, right? The only two poles, they are all negative. So yes, it is BIBO stable. Okay, we're done with the first step. Okay, now that we talk about the marginally stable and the asymptotic stable. Okay, let's start with the asymptotic stable because that's a little bit easy to figure out. Asymptotically, the asymptotic stable, the condition is the pole or the eigenvalues of A have negative real parts. Okay. Alright, so because my eigenvalues, I already mentioned, the eigenvalues of A is, these are diagonal matrix, so eigenvalues of A is just equal to -2, -3, and 0. Apparently, we have one eigen which is 0, which has 0 real parts. So this is not asymptotic stable. Okay. All right. Now let's move to the last one. It's called marginally stable. So marginally stable, because the condition is a little bit weaker than the asymptotic stable. The condition is either eigenvalues of A have negative real parts, or if eigenvalues of A have 0 real parts and those with 0 real parts should have the same geometric multiplicity and geometric and algebraic multiplicity. Okay, that's the condition for the marginally stable. Okay, so either all the eigenvalues of A have negative real parts, which is not true for this case because I already checked the eigenvalues of A, in which one of them is not does not have negative real parts, which is because 0. Or it can have 0 real parts. Now 0 real parts means you can have a 0, but here, okay, but we want to check the geometric multiplicity and algebraic multiplicity. Okay, the algebraic multiplicity, which is determined by the number of eigenvalues. 0 basically, right? Because I only have one. I only check the eigenvalue 0, which has 0 real parts. Now I only have one of them is 0, so which means this is equal to 1. And also geometric multiplicity, which is number of linearly independent eigenvectors for this eigenvalue 0, which is for those with 0 real parts. Apparently, because I must have at least one eigenvalue, non-zero eigenvalue for this eigenvector for the eigenvalue 0. So you must have at least one. So this one you must have one, or you could have more, right? Because the geometric multiplicity the one condition is the geometric multiplicity has to be less than or equal to algebraic multiplicity. You cannot have more than that, which means I cannot have more than 2. I must have 1, but I cannot have more than 1, which means my geometry must be equal to 1. Okay, so this one is 1. Okay, now here, because they are equal, as the marginal stability says, either you have negative real parts or you have 0 real parts, but those with 0 real parts have the same geometric multiplicity and geometric multiplicity, which means here in this case, yes, algebraic multiplicity is equal to geometric multiplicity, which is true. And also the other eigenvalues, they are negative 2, negative 3, they are negative, which is okay. That's why you can conclude that yes, it is marginally stable. Okay, let's move to the next question, which is about the controllability and observability. So question number 6. Okay, so if I give a linear time invariant system, which is given by x dot t, which is equal to negative 1, 1, 0, and 2, negative 3, 0. This is 1. 0, 2, negative 2 time xt plus I have 1, 1, 1 times u sub t, and my y sub t is equal to 1, 1, 1 times xt. So that's my linear time invariant system. So apparently this is my matrix A, matrix B, and matrix C. Okay, so the question is check controllability and observability. Which means we want to check if the system is controllable and observable. Okay, so let's start with the controllability. So for linear time invariant systems, the most typical way for the controllability, check the controllability, is to compute the controllability matrix C, which is given by B, A, B, A square B, so on and so forth, until A n minus 1b. Okay, this n is the dimension of x t basically. So here dimension of c apparently is 3 because I have 3, must have a 3 rows, right? So it's 3. So I only have to compute b a b until a n minus 1. 3 is n is 3, so it's a square b. So that's sufficient enough. Now if the rank of my c is equal to n, which is dimension of x, so this is controllable. If rank of c is less than n, is uncontrollable. So that's basically the condition the condition we can verify the controllability. Okay, now we can move on to the computation of the actual controllability matrix C. So B is 1, 1, 1. So we do A times B. So I'm gonna just you just do the computation. So A times B just give us 0, 0, 0. A square B also give me 0, 0, 0. So this is my controllability matrix C. Apparently the rank of C is equal to 1 because I have only one column which is non-zero. The others are all 0, right? So the rank is equal to 1. It's less than the n. N is 3, right? So it's uncontrollable. So this is uncontrollable. Okay. So now let's move to the observability. So observability is verified by computing the rank of the observability matrix, which is computed by O. O is given by C, CA until CA n minus 1. Okay, again, because n is 3, so it's until CA squared. Okay, so we also have to check the rank. If the rank, the conditions are always is very similar. Is the rank of O is equal to n, so observable. If the rank of O is less than n, so it's unobservable. Okay, that's the condition. Alright, so just have to calculate the matrix O. So C is given by 1, 1, 1. Okay, so 1, 1, 1. So CA, I just want to compute it directly, which is given by 1, 0, negative 1. And CA squared is -1, -1, 2. Okay, so this is a little bit hard to verify, right? So one thing we can check, I don't know what relationship it looks like, is a rank is 3, but you have to check that. You have to is a determinant. You can check the determinant of O. If determinant of O is non-zero, which means it's full rank. If rank is 3. If determinant of O is equal to 0, it's not, is less than 2, 3 basically. Because if they are linear independent, the rank has to be, the determinant has to be non-zero. Okay. If I compute determinant of 0, which is -1, so I can use a second column, a second row. So it is a second column here. Okay, you can do -1, 1 plus 2 time. If I use here I'm using the, I believe I use a second column over here. Okay, so I use negative. The first entry I have is 1. So -1 and 1 plus 2, because the first one sitting on the first row, second column is 1 plus 2, equal to, if I delete the first row and the second column, and I have 1, -1 is 2. Okay. Then we have is plus, because the second one is 0, that we don't care about. The last one is -1, 1 plus, I believe the first, the second row, third is 2 plus 3, which is give us, if I draw the first row and the last column, I have 1, 1, 1, -1. Okay, so if I do stuff like that, so what do I get? Right over here. Okay, let's see. Make sure I do have the right thing. Okay, so this give us, is given by -1 squared is -1, right? This is 1 times 2 minus 1, so this is times 1, plus -1 to the 5th is still -1, and this is 1 times -1 is -1. -1 minus 1, so this is -2, which is -1. This one plus 2, right, is equal to 1. So determinant is non-zero. So this is means the rank of O is 3, which is observable. Okay, so that's what I have for the question number 6. Okay, now let's move to the question number 7. Okay, which is kind of it's about the state feedback control and the state observer design. Okay, so I give a linear system, give a linear time inference given by x dot t, which is equal to 2003 times xt plus 101 time use of t, and y sub t is given by 101 times xt. So here I have, this is the A, this is the B, and this is the C basically. Okay, so my first question is compute, this is find state feedback gain k such that the state feedback control system has -3, -3 as its eigenvalue, which means I want A minus BK as eigenvalues at -2 and -3. So that's my goal. Okay. So apparently I have to check this one. So first one I can mention in class was the first goal is I want to figure out, hey, what's the dimension for k, right? So apparently my k is, dimension is k1 and k2, because I want to do A minus bk, right? Because my dimension for A is 2 by 2, my B is 2 by 1, so my k must be 1 by 2, otherwise I don't have a compatible dimension for A and bk. Okay, so this is, so I assume k is equal to k1 and k2. Okay, the 2 is the 1 by 2. So A minus bk is equal to, write this one, A is 2003, okay, repeat that's one, okay, minus B is 101, K is K1, K2, okay. If I do the product, this one can be computed as 2 minus K1 minus K2 and minus K1 and 3 minus K2. Okay, so let's compute the determinant of lambda I minus A minus BK. That's how we compute the eigenvalues of A minus BK, because I want to assign the eigenvalue of A minus BK at -2 and -3. Okay, so the determinant of this guy is equal to determinant of, this one is equal to lambda plus 2 minus 2 plus K1 and K2 and K1 and lambda minus 3 plus K2. So that's my determinant. So if I do, okay, I don't want to go through too much detail about this one. This one's equal to, let me write down this one as lambda squared plus -5 plus K1 plus K2 lambda plus 6 minus 2K2 plus minus 3K1. So that's my, set to be 0, that's my characteristic equation to compute the eigenvalues A minus BK. Okay, apparently I want eigenvalues A minus BK to be at -2 and -3, which means I want this one start off the same form as lambda plus 2 and times lambda plus 3 equal to 0. If this is the case, if this will be the same as this guy, currently I have lambda is -2 and lambda is -3, which is the one I want to set. Okay, so this one just say if this guy has to be equal as identical to this one, right? So I can just write this one equivalent as lambda squared plus 5 lambda plus 6, meaning that if I have this guy being 5 and this guy being 6, now I'm down, right? So we have to just select this K1 and K2 such that -5 plus K1 plus K2 equal to 5 and 6 minus K2 minus 3K1 equal to 6. That's what I have. This, okay, so it turns out, okay, K1 has to be 4 and K2 has to be equal to 6. So that's the value we figure out. So I don't want to go to detail this one. You can figure out this one fairly easily. Okay. All right. So let's go to the second part of this problem, which is the second part of the problem is I want to design a closed loop state observer. Okay, you can also say is estimator, which means the same, given by is x hat dot t, which is equal to ax hat t plus but plus l times yt minus cx hat t. So that's my closed loop estimator, and one such that A minus LC has eigenvalues at -1 and -2. So the question we're asking for is, yeah, I know what is A, I know what is B, I know what is C, I know whatever. So only the parameter I don't know is L. So the problem is, how do I design L such that A minus LC has eigenvalues at -1 and -2? All right, so let's also start with the dimension of C. So that's the problem. Okay, so let's see what's the dimension. A is 2 by 2 is still, and C is, if you look at C is, go back over here, C is 2 by 1, so it's 2 by 1. So it's 1 by 2, sorry, 1 by 2. Okay, so L has to be 2 by 1, right? Otherwise you don't have the same dimension for A. This two has to have the same dimension. So let's say L is L1, L2. Okay, that's 2 rows and 1 column. Okay, so let's compute A minus LC, which is A is 2003 and LC is minus L1, L2, C is 101. Okay, which is equal to this one is equal to 2 minus L1, you just do everything, minus L1. This is negative L2, this is 3 minus L2, okay. So I want the eigenvalues of this guy to be at negative 1 and negative 2. So let's compute the eigenvalue of this A minus LC, which is given by lambda I minus A minus LC, and you set it to 0. Okay, I don't want to go to the detail of this computation, so you can follow the same procedure I mentioned over here, compute the determinant, and then you write it as lambda squared plus something, right? Times lambda, the similar form. So it turns out this one is equal to lambda squared plus minus 5 plus L1 plus L2 times lambda plus 6 minus 2L2 minus 3L1 is equal to 0. Okay, so I want this one to be equal to what? To be equal to, I want eigenvalue of this guy to be negative 1 and negative 2, which means I want this one sort of given by negative plus 1 and then lambda plus 2. This will give me 2 eigenvalue and negative 1 and negative 2, which is equivalent to say I want this one has a form lambda squared plus 3 lambda plus 2, meaning that I want to have this guy equal to 3 because I want to match this one, this guy equal to 2. So that's what I want to have. Which means I want to find L1 and L2 such that negative 5 plus L1 plus L2 is 3, and 6 minus 2L2 minus 3L1 equal to 2, basically, right? So if you do all the computation, so it turns out my L1 is negative 2L and L2 is 20. Okay, I want to go to detail. You can calculate this one. Two linear equation, right? With 2 parameters, you can find as L1 L2. Okay, now which means you can just replace L and A and B and C as L. So my L is just given by negative 12 and 20. Okay, so that's done. Okay. All right, so that's the question number 7. Okay, let's go to the question number 8. So question number 8 says, give a linear time invariant system given by this xt dot, which is equal to 1, 0, 2, 2, negative 1, 3, and 5, 0, 6 times xt plus 0 to 1 times u sub t, and my y sub t is equal to this. It's 1, 0, 0, 1, 0, 0 times xt. Okay, so my question is, okay, which state, if I let xt be x1t and x2t, x3t, so which one can be directly obtained from yt? Okay, now I just want to figure out which one can be directly from yt, which means if given yt, which you can find which state can be obtained directly from the output. Okay, so if I do some computation over here, because xt is given by x1t, x2, x3t, so you just say 1, 0, 0, 1, 0. So what you do is time x1t, x2t, and x3t, right? So if you do this one, you give us is x1t and x1t. Yeah, apparently my x1t is already, so my output has 2 entries, so both of them are just given by x1t, which means x1t here can be directly obtained from yt. So my yt is a repeat of the x1t twice. That's kind of my output. Okay, so let's go to the last question, question number 9. So it's about an LQR control problem. So it says give a linear time invariant system x dot t, which is equal to 0.5, 0.1, 3, and 1 times xt plus 1 or 2 u sub t. So that's going to give a linear time invariant system. The question is, which one of the following cost function provides the largest penalty on the state xt? So give 4 options. Q is 0.1, 0, 0, 0.1. So and my R is equal to 1. Okay, this is the first one. The B is, the Q is 10, 0, 0, 10, and R is 10. That is also 1. C says, okay, my Q is 10, 0, 0, 1, and my R is 10. My D says my Q is 1, 0, 0, 1, and R is 100. So here my assumption is my cost function is given by 0 infinity x transpose times Q times x plus U transpose Q, R times U. Of course, I drop the t, xt, and xt, xt, ut, ut, okay, over dt. That's my cost function. So x is the matrix I use in parallelize state, basically, right? So what the general principle says, the Q, the higher, which means if it's diagonal one, okay, if Q is diagonal, of course, I also have a assumption is each diagonal entry is non-negative. So I don't have a negative penalize. A negative penalize, which is you promote, you want to have a large one, which is not designed in practice, okay? Then the larger the diagonal entries are, the larger penalty, state penalty we have. So that's the general principle. This also applies to the R. We can also replace this by R, which means if R is diagonal and each entry is non-negative, the largest diagonal entry, the larger diagonal entries are the largest state penalty, or it becomes the control penalty, control input penalty we have. So if we go back to this term, this problem, we want to say which one has the largest state penalty. So which one? If you look at this one, I only care about the R. I don't care about Q. I don't have Q. Not care about R because R is the penalized state control input. So you can just ignore all these numbers over here. It doesn't really matter which value you select. So I only care about R, Q, and the larger the diagonal entries are, the larger the penalty will be on the state. So if you look at this one, so key, this is pretty small. This is large. This is also, these two are the same, but this one is larger than this one, and this also is larger than A, but it's smaller than B. So apparently B has the largest penalty because the diagonal entries have the largest value. So even C has one of them is the same as this one in B, but the second one is not as high as B. So B provides the largest penalty on the state.